Yesterday, we completed electrolysis as a start for the molten systems, and the only industrial process in those electrolysis was extraction of aluminum from its ore bauxite, and this is also known as electrolysis of aluminum oxide. Aluminum oxide's electrolysis is done in molten state and gives us pure aluminum and oxygen. We do get the aluminum. Unfortunately, the oxygen is capable of reacting with the graphite anode as is being converted into carbon dioxide. So we need to replace the anodes after regular time intervals. We studied all of that yesterday, and today we are supposed to start with electrolysis of solutions. The same page has the heading of electrolysis of solutions at the bottom. This is page number 108 from the book. But what I do say sometimes is that electrolysis of solutions is written in somewhat in a complicated manner in the book. So what I tend to tell my students is that electrolysis of solutions can be handled a little bit differently than the electrolysis, the simple one. I mean, the one with the molten systems. So what I'm going to do is that I'm going to head to the document we were working with yesterday. And this document, this started off with electrolysis table for molten, which was pretty easy. All the cations went to cathode, the anions went to anode. And as there was a single cation and single anion, so it was pretty easy to move the cation towards the cathode, anion towards the anode, deposit them over there, and actually work your way out with molten systems. Electrolysis of solutions is a little bit more complicated. Before we start with any of these rules, I want to make sure that you understand in solutions, the stuff gets complicated for us for a certain set of reasons. Let's go through those reasons first. When we talk about a solution, and let's take an example for a better understanding. Let's say I talk about NaCl aqueous solution. So when I talk about NaCl aqueous solution, that means I am telling the students that we are actually getting Na positive ion out of it. And I'm also gonna get Cl negative ion out of it. And this aqueous itself means that water, which we haven't seen previously, but behaves like an ionic compound when electricity is passed through it. Slightly, not completely. Although we do understand that water was a covalent compound, and this is the structure for water. Oxygen has two single bonds with two different hydrogen atoms, and that's how we came up with this formula H2O water. But when in electrolysis systems, when electricity is passed through water, and let me tell you, water is a very poor conductor, pure water. It's actually more like an insulator. But when salts are dissolved through it, water actually becomes a conductor. Salts help make water become a conductor. When it does, water also gets affected by electricity. And this water, which was made from a covalent system, is then converted into its respective ions. Those ions are H positive ions and OH negative ions. These are known as hydrogen ions. These are known as hydroxyl ions or hydroxide ions. So what happens is that we'll get H positive out of it and we'll get OH negative out of it. Water behaving like an ionic compound and being converted into ions, though this happens for a very small amount of water, but it does. And when it does, we actually get a competition. Take a look here. We have two sets of cations. If I separate the cations, I would have Na positive in this system and H positive in this system. And if I separate the anions, I again have two anions in this system, that is Cl negative and OH negative. Which means when I talk about movement of cations towards the cathode or anions towards the anode, I will be talking about two cations going towards the cathode or two anions going towards the anode. And whenever stuff like that happens, and if there are two parties competing against one another, it becomes more like a competition. It becomes more like a race. One has to win, one has to lose whenever it comes to a race, whenever it comes to a competition. So among these two cations, one would win going towards the cathode, and the other would lose, will not be able to go over there. Again, the same is the case with anions. It would be a more like a competition, and one of these anions would win getting towards the anode, and one of them would lose and will not be able to reach over there. So if you take it like a competition, if you understand it that way, I come up with this metaphor to make the students understand that you are supposed to make sure that one of them wins, goes to the cathode and gets deposited over there, discharged over there, and one of the anions goes towards is actually able to win the competition, goes towards the anode and gets discharged over there. You will be able to work with them. But let's say out of these two cations, this one is able to go to cathode, and let's say I am taking it as an example, this one was able to go to anode and was able to win. You'll have two ions left in the system. And those two ions will react with one another. They may form the same thing we started off with, and they may form something new, which actually leads us to a different set of table in terms of electrolysis of solutions. We are going to tell you, whenever we are going to mark a table, we're going to tell you the product at cathode, the product at anode, and the product left in the system, or for other words that we use, left in the system is not a proper terminology. We choose to use the words change to electrolyte. So what happens to the electrolyte? Are some parts of it left from it as a whole? The whole electrolyte is left behind, or it is converted into a new substance? That's how we're gonna go with this table. So what I'm gonna do in this is that I'm going to go for the rules of electrolysis for solutions. We're going to separately study the rules for cations, the rule for anions, so what would happen at the anode, and lastly, we'll study how or what would be left in the system. So coming up next is the part where we'll study cations, anions, and systems separately, so that you are capable of telling me about this product, and this product separately and correctly. The rules coming up next would make sure that you are capable of coming up with all the products of electrolysis in solutions properly. Let's go through that. Starting off with rules for cations. When I use the term rules for cations, I usually come up with one sentence to define it all, that you are supposed to use the reactivity series. And let me tell you, the reactivity series is not present as a part of chapter 4 in the book. It's actually present as a part of chapter 8 in the book. So here's the reference. That's page number 216 of the book. That's figure 8.11. So I'm going to get back to the book. We're going to scroll a little, and we are going to get to the page 216 of the book. On that page, you'll find the reactivity series. Let's talk about reactivity series first. Reactivity series is a series of metals. It consists of mostly metals, but there are a couple of non-metals over there too. Reactivity series is something that is supposed to be memorized by the student completely. So go ahead, take a step, whether you do it phonetically, whether you do it with some fun example, whether you take a help from a fun fact or a sentence, you need to memorize the entire reactivity series. But before you do, in order to make it a little bit easier for you, I actually divide the entire reactivity series into 3 parts for the memorization section to become easier for the students. Let's go through that. If you take a look at the reactivity series, you'll find that there are first 5 elements, then there is an element written in brackets. Remember, if there is anything written in brackets, that's probably a non-metal among the series of metals. So we call it a junction. It is carbon this time. There are a set of 4 more elements over here, and then again, there comes a 1 in bracket, and again, that's non-metal. This time it's not carbon, this time it's hydrogen, and again, that's more like a junction, and we have then a set of metals. There are 4 metals up top after it. So if we look at the reactivity series, it's divided into 3 parts now. The ones on the top of the reactivity series are the ones which I usually say are the most reactive ones. These are 5: potassium, sodium, calcium, magnesium, aluminum. And then there is a non-metal, carbon, after which there are 4 metals. I call them moderately reactive ones. And these are 4. These are zinc, iron, tin, and lead. Then again comes a non-metal, hydrogen, after which we have the least reactive elements. And again, these are 4, that is copper, silver, gold, and platinum. Memorizing reactivity series might not be a problem if it wasn't supposed to be done in an order. As it is supposed to be done in an exact order, and you cannot move an element from top to bottom or bottom to top, that's what makes it more difficult and challenging. So make sure when we are talking about the elements, you write them or memorize them in the proper order. Now, as I was saying, let's get back to where we were on the other page. As I was saying, that reactivity series is used for cations. Remember, for every cation, the cations would be in such a way that they will also always contain a cation that is competing against the cation of water, because solutions are always made in water. So one of the cations would be a metal ion, but it would always be competing against H positive or hydrogen ion. So what happens is that we need to make sure that we can compare every cation on the list with hydrogen. Take a look. Hydrogen is present at the second junction. It's actually more towards the lower part of the reactivity series. If I am to compare the rest of the elements of the reactivity series with hydrogen, I would find most of them to be more reactive than hydrogen. The only ones that are less reactive than hydrogen in order are copper, silver, gold, and platinum. Let's talk about the first rule of electrolysis. The more reactive one stays inside the solution, the less reactive one go to the respective electrode. This is the most basic rule for cations or anions in solutions. I repeat, the more reactive one stays in the solution, the less reactive one gets attracted to the respective electrode and gets discharged over there. If we are to compare everything with hydrogen, and only the less reactive ones can get to the respective electrode cathode, then the ones who would always be successful in this competition against hydrogen would be the ones that are less reactive than it. Of course, the ones at the bottom of it, which are copper, silver, gold, and platinum. These 4 are the only ones which are less reactive than hydrogen, and in any kind of competition, they would be able to get to the cathode and gets deposited over there as metals. Copper ions as copper metal, silver ions as silver metal, so on with gold and platinum. For anyone apart from these 4, as they are more reactive than hydrogen, they won't be able to get to the respective electrode. They would stay inside the system, and hydrogen would be able to go to the respective electrode. Which means most of the time when we are dealing with solutions, if the solution is made up of the following elements, and hence we come to our first rule. If the salt name or the formula contains elements such as copper, silver, gold, or platinum, they are deposited at the cathode. Otherwise, every single time hydrogen gas is produced at cathode. And the formula or the equation for hydrogen gas is that two hydrogen ions receive two electrons. As this is cathode, it's supposed to be a reduction reaction. So two hydrogen ions plus two addition of electrons gives us hydrogen gas. So most of the time, let's say we are working with sodium salt or potassium salt or magnesium salt. Let's say we are working with an iron-based salt or a zinc-based salt. As all of these elements are more reactive than hydrogen, so none of them would be able to leave the solution. They will always stay inside the solution. Hydrogen ions instead would be able to get to the cathode and gets a discharge from there in the form of hydrogen gas. So as all of these are more reactive than hydrogen in comparison, so they would stay inside the solution. In this case, we started off with the example of brine solution. The student has spelled it incorrectly. It's actually B-R-I-N-E, brine. And this is not NaCl2 aqueous, it's actually concentrated NaCl. So in this case, it would be sodium ions staying inside the system, unable to get to the cathode, and hydrogen ions would be able to get to the cathode, would win, as metaphorically speaking, and will get discharged as hydrogen gas. So that's pretty much the rules for cations. It's actually a single rule. If the formula contains the elements such as copper, silver, gold, or platinum, they would get discharged as metals. Otherwise, every single time, whatever metal our substance is made up of, our chemical or salt is made up of, hydrogen would be released or produced at cathode as in the form of hydrogen gas. So I think it's pretty easy to remember. That's all we need from the reactivity series. So we're going to move forward. Are we clear with the cation rule? Okay. Rules for anions. Anions can actually be divided into two categories. So let's not do it through this paper. This paper is written in words, which becomes somewhat a little bit difficult. So I'm going to open up a whiteboard screen and we're going to do it from there. So if I talk about the rules for anions, the rules for anions are a little bit more complicated than the rules for cations. So we're gonna talk about the anions. Anions can be divided into two categories: simple anions, which really consist of just one atom only. For example, chloride ions, bromide ions, or iodide ions. The second category are polyatomic anions. Polyatomic, as the name suggests, contains more than one atom in an anion, and these can be nitrate ions, sulfate ions, phosphate ions, maybe carbonate ions, or hydrogen carbonate ions. So these are the anions. As I've previously discussed, water is divided into two parts, and the anion that we get out of water is hydroxyl, OH negative. So every kind of anion we have written here on the list has to compete against OH negative. So they might have to compete with against OH negative, or this might has to compete against OH negative. If it happens, then what are we supposed to do? Let's bifurcate the rules, because rules for simple anions are different than the rules for polyatomic ions. The rules for simple anions are actually concentration dependent. So in this case, every time we are going to require the concentration of the salt solution. As a revision, let me remind you that there can be two types of solutions regarding concentration. Concentrated solution, one that contains a higher proportion of solute, and dilute solution, one that contains a lower proportion of solute, or otherwise you can say a higher proportion of a solvent. So what happens if it's concentrated? For concentrated halide solutions, halogens are formed at respective electrodes. So at anode, instead of writing respective electrode, let's write anode. So at anode, chloride can form chlorine gas, bromide can form bromine liquid, or iodines can form iodine solid. So halogens are formed Cl2, Pr2, or I2 would form depending upon the case, whichever ion is present in the system. For dilute solutions, for halides, oxygen in the form of O2 is formed at anode. And for the formation of oxygen, there is an equation for which the reasoning is never given at this level. We only ask our students to memorize the equation. The reasoning is not a requirement of O levels. It's actually beyond the requirements of it. It's just that we write the equation and we ask the students to memorize it. So I'm going to write the same equation. 4 OH negative ions would go to the electrode, would form 2 water molecules after the reaction, would form a molecule of oxygen, and will give out 3 electrons as a part of oxidation reaction. So these aqueous ions give us a liquid and a gas and 4 electrons. This is going to be the equation. So it's pretty easy. If our salt contains a halide and it has a concentrated solution, a halogen would form at anode. But if our salt contains a halide, but it's a dilute solution, as there is excess of OH negative ions, they would be successful in getting to the anode, forming water, which already was a part of the system. So isn't considered as really a product. It was already there. It was already present as a part of the system. Oxygen is considered as the product at anode, because that's something different. So for polyatomic ions, as all polyatomic ions are more reactive than hydroxyl ion, they tend to stay inside the system. When they stay inside the system, oxygen is formed at anode, and by the same reaction. So I'm going to repeat this equation. 4 OH negative aqueous gives us 2 H2O, 2 water molecules as liquid, plus O2 oxygen as a gas, plus 4 electrons. The gas can be shown by an upward arrow, means it would bubble out of the solution. So for polyatomic ions, it's bound to happen that all of them are more reactive than hydroxide ion. They all stay inside the system. They can't leave the system. They can't go to the respective anode, and hydroxide ion always gets successful in getting to the respective electrode anode, and hydroxide ions are converted into water, which is a part of the system. We don't really consider it as a product. So the product is considered to be oxygen. This is an oxidation reaction because 4 electrons are lost in this reaction. This is pretty much the rules for anions. So what are we going to keep in mind? If that's a concentrated halide solution, only then something else would form at anode, chloride, bromide, or iodine. If that's a dilute halide solution, or if that's a solution with polyatomic anions, oxygen would form by this equation that you are about to cram from now on. And with the help of this equation, you're going to prove to the examiner that it's the oxygen that is produced most of the time at the anode, whether the cases of polyatomic ions or whether the cases of halide ions in dilute solutions. I hope that explains it. So let's stop sharing over here, get back to the page we were at, and you'll find the same set of rules over here. So simple anions versus OH, the student has written it a little bit with incorrection. That's not right. Depends upon the concentration. If the solution's concentrated, halide goes to the anode and halogens in diatomic forms are formed. If the solution is dilute, then OH negative goes to the anode and oxygen gas is formed by the given equation. Polyatomic ions are more reactive than hydroxide ions, so they always tend to stay inside the solution. So OH negative or hydroxide ions are always capable of getting to the anode and released as oxygen gas. So if the salt name consists of concentrated halide, only then the halogens is produced. In all other cases, oxygen is produced. So if I summarize both cations and anions, only in the case if the cation is copper, silver, gold, or platinum, something else would be produced other than hydrogen. In all other cases, hydrogen is produced. In case of anions, only when the case is a salt with a concentrated halide solution is a halogen produced at anode. Otherwise, it's oxygen every single time produced at anode. So electrolysis of solutions is actually not very difficult. It's pretty easy because there is only a single case in terms of cations and a single case in terms of anions, whereas something else other than hydrogen at cathode or oxygen at anode is produced, respectively. All right. So let's take a look at the solutions, and with these examples, we're going to understand our products at cathode, of course, due to a reduction reaction, or product at anode, of course, due to a oxidation reaction, and change to electrolyte. Change to electrolyte is an important column when it comes to electrolysis, because this tells us whether we're going to make something new out of it, or we're going to stick with the same system or solution, or we can say in between the salt and water, which one electrolyzed and which one stayed. Let's take a couple of examples to understand it. Concentrated sodium chloride solution, brine solution. It gives us Na positive ion and Cl negative ion. Aqueous system will give us H positive ions and OH negative ions. The student hasn't written all of the ions, but I always insist my students to write all 4 set of ions. As soon as you see a name, write all 4 set of ions. So you can take one of these ions to the cathode, one of these to the anode, and whichever 2 you're left with, you react them together to form the change to electrolyte. Take a look. Hydrogen goes to cathode as it's a concentrated chloride solution. So chlorine goes to anode. 2H positive plus 2 electrons gives a hydrogen gas. As sodium is more reactive, it's going to stay inside the solution. Let's keep it for the change to electrolyte part. For chlorine, 2 chloride ions, the negative sign is missing, gives us a chlorine molecule plus 2 electrons. This is an oxidation reaction which gave us chlorine gas at anode. Since we are left with Na positive and OH negative, what's not written over here is that this Na positive and this OH negative ions will react to form NaOH aqueous solution. That's how we come up with a change to electrolyte. That's how we can say we formed sodium hydroxide at the change to electrolyte. So writing all 4 ions over here will help you take one of them to the cathode, the other one to the anode, and whichever 2 ions you're left with can be the same, can be different, will give you something new or something same at a change to electrolyte. Let's go with the dilute NaCl example. As soon as we have a dilute solution, this time we'll add a very little amount of NaCl to a large amount of water, we'll get a dilute solution. And what would happen? The set of products that we get are different. Take a look, we get hydrogen. I'm going to write all the ions over here. This H positive ions went to cathode and gave us hydrogen. Instead of Cl negative, OH negative ions went to anode and gave us oxygen. We are left with Na positive and Cl negative, and they both reacted with one another again to form the same sodium chloride we started off with. So the products at cathode, anode, and change to electrolyte for concentrated solution and for the dilute solution are different. We have the same hydrogen gas at cathode, but the anode product is different. We're producing chlorine gas at anode in case of concentrated solution and oxygen gas at anode in case of dilute solution. We're producing sodium hydroxide solution as a change to electrolyte. However, the sodium chloride salt is left if we are going with a dilute solution. So for the dilute solution, pay close attention. Water has been electrolyzed into hydrogen and oxygen gases, and the salt is left. So if you have a huge amount of water and a little amount of salt, keep adding water into the solution, the salt will remain over there, and water will keep getting electrolyzed to give us hydrogen and oxygen as products at cathode and anode, respectively. This can happen with almost any kind of salt except for the salts of copper, silver, gold, and platinum. So you would find that concentrated potassium iodide gives us hydrogen and iodine at cathode and anode, and potassium hydroxide, this is not oxide, this is potassium hydroxide as a change to electrolyte. However, if we have a dilute solution of potassium iodide, we produce hydrogen and oxygen at cathode and anode respectively, and potassium iodide is left in the same way as sodium chloride did as a change to electrolyte. That's what I was talking about for dilute salt solutions. They electrolyze the water and they remain in the same amount, almost as the same amount in the system or the solution. Let's go with more examples. Sodium, silver. Let's go with an example of silver. Silver nitrate has been a common past paper question when it comes to electrolysis of solutions. So let's focus on this one first. Silver nitrate, silver stays in the system and gives us silver. The entire equation is wrong, my bad. The student has completely written a wrong equation. Silver is actually present in the positive 1 ion. It only takes up an electron and is converted into solid silver, which is deposited at cathode. We get oxygen out of the hydroxide ions, and hydrogen and nitrate ions combine to form the nitric acid as a change to electrolyte. So we get something new as a change to electrolyte. Silver is deposited at cathode, oxygen is produced at anode, and nitric acid is what's left in the system. So this is a different example, a really different one when we talk about silver nitrate. Concentrated hydrochloric acid and dilute hydrochloric acid have always been a part of past paper examples, books, reference books, all of them. This is the same acid, but when taken in concentrated dilute forms, really change the products. We only get hydrogen at the cathode because there is no other cation present in the system. We get chlorine gas in concentrated solution case at anode and oxygen in the case of dilute solution. We get water as a change to electrolyte, but we get hydrochloric acid as a change to electrolyte in concentrated and dilute systems respectively. So this one is considered because in concentrated system, the acid gets electrolyzed, water remains in the system. In dilute solution, water gets electrolyzed and acid remains in the system. That's why this example has been important in past papers as well. Moving on, let's talk about the example of copper sulfate. Copper sulfate has also been an important example when it comes to electrolysis of solutions. Copper ions with +2 charge gain 2 electrons and are deposited as red-brown copper metal on cathode in the solid form. As copper is less reactive than hydrogen, it is capable of getting to the electrode and gets deposited over there. Hydrogen stays as a part of electrolyte back in the system. The hydroxide ions, as sulfate ions are more reactive, they stick in the system, and hydroxide ions go towards the anode and form oxygen over there. So we are left with hydrogen ions and sulfate ions, which actually react with one another. Two hydrogen ions plus sulfate ions would be able to give you sulfuric acid as a change to electrolyte. So this is also an interesting example. We wind up with an acid in the system. Well, we never started off with it. So this blue colored solution, copper sulfate, usually goes pale and acidic at the end of the electrolysis because red brown copper is deposited at cathode and a colorless gas bubbles out of at the anode, oxygen. When I talk about it like this way, let me tell you all visible observations in electrolysis have also been a part of past papers in IGCSE chemistry. That's what actually makes the solution a little bit tougher. You don't just need to go with the background chemistry according to these tables. You're also supposed to talk about the visual observations. Copper sulfate is a blue colored solution. When you move along with the electrolysis, the color of the solution pales. So it becomes lighter and lighter because copper, a red-brown metal, deposits at cathode and a colorless gas bubbles out of the at anode. A colorless solution is left as a change to electrolyte. The color pales, it becomes lighter and lighter, and we end up with a colorless solution which is more acidic than the one we started off with, which can always be confirmed with the help of an indicator paper. A pH paper can do the trick. Damp blue litmus paper can be turned into red to detect this sulfuric acid solution that we are left with at the end of this electrolysis. So when I talk about it, I tell my students that copper sulfate, silver nitrate, hydrochloric acid in concentrated and dilute forms, sodium chloride or blind solution in concentrated and dilute forms have been an important past paper question in electrolysis of solutions. So you'll find many other examples from past papers over here and their possible solutions, but make sure you check their questions carefully. There are many mistakes in this document, as this is made by the student and then never got the time to check it and correct it. So there are many mistakes. As many mistakes as I saw myself while doing this work, I tried to correct them or tell you about it, but keep an open eye. There might be some more mistakes over there. And this completes our electrolysis in solutions. Well, this doesn't complete our portion in the book. Well, let me get back to the chapter 4. So, as I was saying, that electrolysis of solution starts off at 108. Then they talk about what happens at the cathode or what happens at the anode. The first example starts with electrolysis of concentrated sodium chloride solution. If we do it in lab, we do it in the form of these inverted test tubes. Inverted test tubes are a good way to capture the gases, as this electrolysis produces hydrogen gas at cathode and chlorine gas, which is a pale green gas, at anode. This is a good way to do it. So if you're supposed to draw diagrams for this one, for any system that produces both gases at cathode and anode, inverted test tubes can be used. If it does not produce a gas at a specific electrode, you don't need to use an inverted test tube over there. So while performing it in lab, we get hydrogen at cathode, chlorine at anode, and sodium hydroxide solution as a change to electrolyte. But if we talk about doing that in industry or on a larger scale, membrane cells are considered to be the most modern of the system. A membrane cell has a titanium anode, a nickel cathode, hydrogen won't attack nickel, chlorine won't attack titanium, so they are chosen for their respective electrodes. electrode materials. Anode and cathode compartments are separated by a membrane. The membrane is selective, partially permeable. That means it allows sodium ions and water to flow through it, but no other ions. This means that the hydroxide ions can be kept separate, and products are kept separate and cannot react with one another. Take a look. Brine comes in from the left. We have this anode compartment, then a membrane, and the cathode compartment. Cathode compartment gives out a colorless gas. Hydrogen is going out of the system. Anode compartment gives us a pale green gas. Chlorine is going out of the system. Sodium ions pass from this side along with water onto the other side. That's why the other side is in a dark blue color as compared to the lit compartment. And as sodium ions move onto this side, they react with hydroxide ions, form sodium hydroxide, which is taken down as a solution and separated out of it. This is an ion exchange membrane. It only allows sodium ions and water to pass and block the rest of the ions to move from one side to another. Sodium hydroxide solution is moved and is further purified. So this is a way to form sodium hydroxide in industry. Electrolysis of acid solutions actually is going to prove to us how we electrolyze water to our own use. When we are supposed to electrolyze water, we do that with Huffman's voltmeter. This piece of apparatus actually uses dilute sulfuric acid in order to electrolyze water. Dilute sulfuric acid would only make water as a conductor, would stay back as a change to electrolyte as dilute sulfuric acid, and water would be electrolyzed to give us hydrogen at cathode, as you can see over here, and oxygen at anode, as you can see over here. What's noticeable and has been a part of past papers is that you are going to see the volume of hydrogen is double than that of oxygen. That's because the formula of water contains 2 atoms of hydrogen, will give you more hydrogen than it does oxygen. So the 2:1 withstands in their volume as well. That's why we have double the amount of hydrogen than we have oxygen. This has been a common question in past papers when we talked about Huffman's voltmeter, electrolyzing water to get hydrogen and oxygen. However, this is an expensive way for getting hydrogen and oxygen. This completes for us the electrolysis of solutions as well as the industries related to it.